faculty at Carnegie Mellon University, and he's also chief scientist at Cartesia. I think you probably have heard his name many, many, many times this week, as well as in the reading groups. He's one of the chief architects of these architectures like S4 and Mamba. And so today he's going to tell us a little bit about the trade-offs of state-space models, and I'm looking forward to his talk. Albert, take it away.
Thanks, Andre. Okay, sounds like this is on. Thanks for coming, everyone. So today I'm going to talk a bit about kind of a high-level way of how I think about different types of sequence models and trade-offs between transformers and other types of models such as state-space models. This is going to be pretty similar to a workshop talk I gave at ICML. So if you've been to those, don't expect too much new, but I've kind of refined presentation of some of it. So in the last year, we've seen a resurgence of lots of different types of linear models like recurrent models, RNNs, and what are now called popularly called state-space models or SSMs. There's been many, many types of these from RetNet, which was kind of a year ago, refinements of the LSTM called the XLSTM, lots of other models like DeltaNet, TTT, the RWKB series. There's all sorts of others. You may have heard of Based earlier this week. And of course, there is Mamba and Mamba 2. And so a lot of these models share a lot of the same commonalities between them. And they kind of have a lot of the same core principles. So what I'm going to talk about today will apply to kind of this whole class of models at large. You can kind of think of them as either recurrent models or linear time models, RNNs or SSMs. They all kind of refer to a lot of the same things. So I'm going to be talking about, I'm going to call them state-space models in particular, and kind of illustrate some of their main concepts, particularly illustrated through the Mamba model, but a lot of them are pretty similar and apply more broadly. We are going to also be thinking about the paradigm of autoregressive modeling primarily. So this was kind of popularized by the GPT series of models. This is how large language models are trained, and so I think we're all probably pretty familiar with these. And so these models, at least the way they generate, is one word or token or sample at a time. This can apply to language data, which is where it's most commonly used, but it can apply to any sort of sequential data as well. So this is just a general paradigm for factorizing generative models over sequences. There's also two distinct regimes for autoregressive models where inference and training work kind of differently. At inference time, you generate tokens one by one. And at training time, you kind of just use a general sequence-to-sequence mapping. Okay, and so the main models we're going to look at are, and by the way, feel free to interrupt me with questions throughout this talk. I think I have some extra time. So just raise your hand or shout out if you have a question. So at a high level, I think we're going to be talking about transformers and these linear models. So transformers, of course, basically work by given any sort of prefix or prompt, they try to generate another word by comparing it to every single previous word that has appeared in the sequence. And so it generates words one at a time like this. If you add up all of the operations or comparisons it's making, that will be a quadratic number in the sequence length. So it's commonly said to scale quadratically in the sequence length, or linearly at inference time, each step is linear in the sequence length. And in SSMs or recurrent models in general, the paradigm is kind of different, where the tokens stream in and into a constant state. The state represents a summary of everything the model has seen, and kind of the individual tokens are discarded and only accessed through the state. And through the state, then this is the object that interacts repeatedly with the environment or with new generations, with new data as they come in. And the model can generate or process new data online at every time step in constant time. So over the whole sequence length, it takes linear time. So this is kind of one of the main obvious differences is this quadratic versus linear time. I'll get back to this later in the talk and talk about how I think this is kind of not really the right way to think about it, but okay. So so just to kind of be on the same page. So when we're talking about autoregressive models using sequence models, the way I normally define a sequence model is very simple. I basically define it as a black box parameterized transformation from an input sequence to an output sequence. So typically, basically, you can think of it as a module that takes in an input of a specific shape, which can have extra channel dimensions, batch dimensions, and so on, and returns an output of the exact same shape. And the key, the thing that characterizes a sequence model is that this black box has to do some sort of mixing across the sequence axis, in contrast to pointwise modules like MLPs, feed-forward networks, and so on, which we'll kind of ignore entirely today. There's many types of large families of sequence models, from attention, of course, and RNNs, as well as like convolutions, ODE-based models, lots of other things. I think these kind of generally capture the main characteristics of all the types of popularly used sequence models. And so all of them have basically the exact same interface. You can interchange any of them for any other. And then the only question is, what are they doing differently? What are the trade-offs between them? And so the main concept that we're going to use to try to get to this question of what are their trade-offs is, I claim that you can basically understand a lot about these models by examining what is in their autoregressive state. And no matter what sequence model you're using, all of them have this concept of an autoregressive state. So what is that? Well, basically, if you're using any sequence model autoregressively, in some sense, you can think of them as a quote-unquote state space model, in the sense that there is a state that is evolving through time. So these terms are very loose, and in fact, the term SSM, I have this whole other rant aside for this, but it's very not descriptive. So people often get confused when you use this term, but nowadays we often use it to refer to a specific class of models like Mamba and so on, but broadly refers to any model that kind of has a state that evolves through time. And so when you look at an autoregressive model, these models also have an implicit state. Any model, basically, if you think of as it's generating tokens, basically you can just ask, what is the model storing in memory in between each token? And so that is going to be its autoregressive state. And so any one of these sequence models that we've kind of illustrated all have this concept. So let's take a look at the main families that we're going to look at. So recurrent neural networks, RNNs, a very general concept where basically they are defined by, usually defined through this formula, where basically the definition is basically that there is some hidden state, often denoted H. There's a hidden state at each time step, in between time steps, and the model is characterized basically by how is this state evolving through time based on each incoming input. So basically, these models basically will unbind the sequence across the time axis, process the inputs one at a time. I'm going to use X to refer to inputs. And then there's any parameterized function that combines the current state with the last state with the current input to produce the next state. Any one of these models can loosely be thought of as an RNN. And this is kind of the most general way to process sequences. So a little more specifically for RNNs, we will think of this hidden state as being a fixed size vector. Otherwise, even like attention or anything is going to be an RNN again. So these are very generic concepts. But the way to distinguish them is going to be what is this transformation function or the combination function. There's a lot of classical RNNs, in the past the oldest ones kind of would just use a linear update here with a nonlinearity. LSTMs were the most popular one for a while, which adds some more features. But we're not going to talk about those. So the modern type of state space model is basically a specific, you can view it as a specific type of recurrent model with a specific update, where the update function is, again, going to kind of be like a linear combination of the previous state and the current input, governed by these transition matrices A and B. And so the hidden state update is the most important part of the model. There's also how do you turn this state into an output through another projection, which is going to be, we won't focus on that. But one way that these differ a little bit from traditional RNNs is that the hidden state size is a lot bigger than the input size. So these particular set of equations you can view as a transformation from a one-dimensional input to a one-dimensional output through a larger latent state. So this is kind of related to the name, why they're called state space models. But basically, the shapes of these matrices are defined in a way so that the input is expanded into a larger state. This obviously satisfies the normal definition of an RNN, but traditionally RNNs don't really have this feature. So this is basically just the general kind of formulation of a modern state space model, and there's many variations you can do on these depending on how you define these matrices and so on. Yeah.
The fact that the latent variable is so large, isn't that just a coincidence due to the fact that you were competing with a transformer?
I'm not sure I'd call it a coincidence. I mean, so it is a intentional way to design the model. But I'm not sure how to interpret this question.
That if we were to convince any other variant and we were trying to compete with a transformer, we would have to make its size large in order to compete with transformers.
Yeah, so I mean, the reason why the state is large is an intentional design choice, because when you kind of realize that the role of the state and you need it to be large, then sure, like if you wanted to have transformer-like capabilities, then you do need to expand the state. So I mean, it sounds kind of obvious, but at the same time, this is something that no one really did before, right? When RNNs were very popular. So yeah, so let me elaborate on this a little bit. But okay, so this is just like a very kind of high-level definition of the state space model. And so we kind of define them through this equation. Often, like, these models are thought of as being characterized by the update function, like this function. But kind of a more interesting way to think about them, excuse me, is that you can also perhaps define these models from first principles through their autoregressive state. So as I define, the state is what is the model remembering in between time steps. And here, kind of illustrated in blue, is this state. It's basically a fixed size vector. And one could have basically like turned this definition on it, or the characterization on its head, and instead of saying this is how the model is defined, you can say that the model is characterized by being basically models with fixed size state vectors. So this is basically how we're going to think about them. And the trade-offs of these models can be revealed through this characterization. So the main advantages of these models is, one of the main advantages is the efficiency. There's kind of some other advantages in, say, inductive bias and so on. But for example, the efficiency benefit of these models is basically directly related to the fact that they have fixed size state vectors, right? So that's what gives it constant time per step, or linear time over a whole sequence. And similarly, their main weaknesses is that for a long time, any of these recurrent models were performed much worse than things like transformers on certain modalities such as language, which can be viewed as because on information-dense modalities like language, where you might have to, in order to work with the task you care about, you might have to remember a lot about the past. Then the fact that you only have a fixed size state that is summarizing everything in the past means that your model might have a kind of a representation issue or capacity issue. And so compared to attention, along this axis of what is in the state, you can view attention as being on the exact opposite extreme, where unlike SSMs, which can be characterized as models with fixed size states, attention is basically a model with infinite size states. Or state space models basically do strong compression of the data into your state, whereas attention is explicitly doing no compression. So, question. So we're talking about kind of the autoregressive modeling regime. All of these models, you can adapt them to bidirectional settings, or yeah. So this is we're talking about causal attention, or like I guess people call them decoder transformers or something. Right. So here, like, what is the state of an attention? You don't normally think of these as stateful models, but if you're actually thinking about what is the model remembering in between time steps, it does have a memory, and that is what's commonly known as the KV cache. But but we don't even need to talk about the details of how attention is implemented. You can kind of abstract this away and say that because of the way attention is doing pairwise comparison between every pair of positions, in order to do that at inference, when you see a new piece of data, in order to do that and compare it to every single past piece of data, that means that we had to have explicitly cached everything in the past, right? So kind of just at a high level, just based on the definition of this pairwise comparison thing, you can say that this model needed to have cached everything it's seen before. So that's the KV cache, and so basically it is explicitly representing some representation for every single time step in the past. And so this is what gives it its benefits. It is kind of doing lots of work. It's modeling all connections between data. It can kind of skip over past things and directly model long-range dependencies. But this is also what leads directly to its kind of linear time inference and quadratic time training. Okay, so basically, just looking at what is in the state of these models, basically, at a high level, kind of characterizes what they're good and bad at. Okay, so let me say a little bit more about the work on the efficient model front, like the linear model SSMs, to make them more effective. So to me, basically, there were 3 key ingredients that were needed to get these models to perform a lot better. So this is kind of the difference between, say, the older LSTM versus modern SSMs. So I'll illustrate this through the lens of Mamba, but the main ingredients are basically the state size, the state update function, and the efficiency of the models. And so the state size is basically, as we kind of talked about, how large is the autoregressive state. So basically, if you kind of are thinking of this, if you're thinking through the lens of the autoregressive state, then you kind of realize that you just need larger states to be able to have larger capacity and work on more difficult tasks. And so this is a key difference of these models, where there's kind of a controllable parameter that we usually call n, which expands the dimension of the input by a large factor on the order of 100 or something. With all of these ingredients as well, they kind of have been used in various other related models. For example, linear attention, which was a few years ago, can be viewed as a type of recurrent model. It's actually very related to SSMs as well, that has this state expansion feature. The second question is that having a large state isn't enough. Your model needs to be able to control what is in that state, right? And so this is kind of a weakness of other things like linear attention. And so you want your model to have finer grained control over what is in its state. For that, you need to define a update function that is kind of expressive enough. And so the way that this worked in Mamba is what we call selectivity. It's very, very related to the older gating ideas in RNNs. And basically, it just means that in the context of SSMs and Mamba, basically it means that these transition matrices can themselves depend on the input, so that depending on the input, the model controls whether to let it into the hidden state or not. So this is there's many variants of these that you can do, but you kind of need something along these lines in order to get more expressive states for information dense modalities. And then the final ingredient is that with larger states and more expressive state updates, your model is more expressive, but then the downside is that it might be harder to compute them. And this is, again, another big issue with classical RNNs, because they're sequential and they're not easily parallelized on GPUs and TPUs. And so you have to also design a model in a way such that it can actually be computed fast in practice on our current accelerators. So what Mamba did was it basically purposely linearized these models in a way that it removed the nonlinearities, which actually has a lot of benefits, but one of them is that you can then compute the model really fast in a forward pass. And later versions of these models, like Mamba 2, actually did even rewrote the models even more, so that you can actually rewrite large parts of it as matrix multiplications, and this really allows you to compute it fast on GPUs. So you can kind of view it as, with these sort of models that have no nonlinearities in the time dimension, you can sort of unroll the models like on paper in closed form, and then find more clever ways to compute all of it ahead of time at once. So these are the main ingredients, I think, and all of them have kind of been touched on in various related other models. Question.
So the C subscript of the parameters suggests like it's changing by time step. But can you break that to like some parameter sharing? Is it because you're writing NT because it's a bunch of inputs, so that's getting across every time step, or?
Yeah, so this is changing across every time step. In fact, you need this really to not just be a function of time, but actually of the input. So I don't have the full notation that's revealing that, but yeah. So I'm not sure. You said something about parameter sharing. I didn't catch that.
Sharing across time steps is like
so kind of like there's some weights that are the same across time steps, and those weights will take this input and turn it into this parameter. So this parameter depends on the input, and then that decides kind of whether to let the input in or not.
Yeah. But the crucial just depend on the XTs, right? Not on the HTs.
Yeah, so these particular models depend only on XT. They would be even more expressive if you could depend on the hidden state as well, which would probably be helpful. But they're kind of defined in a specific way for the efficiency as well. So there's a bunch of trade-offs there that I'm kind of not getting into details.
What is the reason for restricting the state or the output X to be one-dimensional?
So this is kind of just how the models are defined. You could make them higher dimensional in here. So there's like all these variants of state space models, like multi-input, multi-output, single input, single output.
Don't you need, when you're doing the prefix scan, don't you need to keep track of the whole matrix anyway?
Which matrix?
Ultimately, this is going to be implemented as, for each token, you're going to output a matrix, and then the output at each position is just going to be the product of all the matrices up to a certain point.
Sure. So
So you need to keep track of the matrices, not just vectors when you're
yeah, so it depends on how exactly you're parameterizing these, how you're computing them. So there's so an additional thing you need is that you need these matrices to kind of be more structured so that you can do this more efficiently. A very popular structure to impose on these are diagonal matrices so that you can kind of view each channel independently. You'll still need to kind of carry a lot of vectors in memory. And then there's a lot of other kind of tricks that you do, or like computational techniques to make this fast enough. Yeah. Yeah, so I kind of wanted to abstract away a lot of these details because there's lots of variants that you can do on these models. So this is kind of the next point, which is that since Mamba, there has been probably like a dozen other models with different types of state update functions, like variants of these. And my opinion is that a lot of these have basically reached kind of similar, they all kind of like perform quite similarly. And they all basically, as long as you have these three key ingredients, your model that's kind of like squeezing the most performance that you can out of these these models with kind of like bounded autoregressive states. You can keep playing around with like more efficient update functions and so on, or more expressive, but they feel kind of quite similar in downstream performance. So here is basically a reference to a very nice table by Songlin Yang, who has done a lot of really good work in this space. So it kind of summarizes a lot of the differences between these. But as I said, so I think a lot of them are quite similar. And so the next thing I want to talk about is that kind of going back to the what's in common to all of these, which is what are the fundamental trade-offs that this whole class of models has against attention. And so, so to answer that, once again, we can kind of, one way to think about it is through this lens of what's in the autoregressive state, this contrast between models that attention, which does no state compression and caches a representation for every token, versus models that do strong state compression into a finite state vector, which basically these have opposite trade-offs along the efficiency to performance axis. Okay, so now talking more about these trade-offs. So one kind of very coarse analogy I sometimes like to use, if there's any neuroscientists in the room, don't yell at me. But so we kind of had this overview of these models where we said transformers kind of do this quadratic generation by looking at every past token, and state space models stream tokens in and only interact with data through the state, right? So a coarse analogy that you can kind of use is that transformers are kind of like a database. So if you look at what it's doing as an autoregressive model, it has this KV cache. It's storing kind of an explicit representation for every token you've seen. That's kind of like a database of all the data you've seen. And then for every new piece of input, you kind of look over your entire database. You compare it to everything you've seen so far, and work with that. And recurrent models, SSMs, are kind of like more like a brain in the sense that like the brain kind of interacts with the world in this streaming fashion where you don't explicitly remember things in the past, but you've taken everything you've like seen in your life and compressed it into a finite size representation. Of course, the brain's very, very large and expressive, but it has that same concept, right? And so some of the trade-offs of these models are very similar to the differences between database and a brain. So for state space models, the benefits again are that they're a stateful model. They've done compression of data into this state. They're very fast in interactive settings and any online setting. And I think there may be some more subtle benefits, which is that by forcing you to compress your data into something smaller, it maybe forces the model to kind of abstract away the key high-level understanding or high-level abstractions. Whereas the downsides are that it kind of has obvious drawbacks in that if you have a finite size state, you just can't remember certain types of information, right? You can't do some sort of like exact lookup, exact copying type things. So any sort of tasks that involve recall, retrieval, these like multi-query recall problems, needle and haystack, become a lot harder for these models. And this is kind of actually very similar to the trade-offs in what a human brain can do. It's good kind of like summarization and understanding of things, but bad at exact memorization of like a dictionary or of long strings of stuff and so on. And kind of as an aside, I think that a discussion that a lot of people have had are that our current evaluations are not very nuanced in some ways. And for example, if you look at like one of the benefits of these models that is sometimes espoused is that they can, in some sense, handle infinite context or very long context because the models scale better with sequence length, right? And of course, there's a downside to that, which is that you can computationally handle long sequences, but are you actually processing that data in a sensible way? Are you like actually able to remember anything in it? And so these long context benchmarks have kind of are very there's a lot of kind of nuance that can be lost in benchmarks, and evals are in general a hard problem. But one thing that's kind of been noted is that long context benchmarks right now are very heavily focused on more easily measurable things, which are very retrieval focused. Things like needle and haystack, where you can kind of like very easily define a task and measure one thing. Even things like question answering, which is a very popular long context thing because it's easier to define, is very heavily retrieval focused. Whereas some sort of like fuzzier notions of understanding and reasoning and so on are much harder to measure. And those might actually be sort of qualitative differences in these types of models that these compressive models might be better at compared to retrieval-focused tasks. These are things that kind of the whole community still doesn't really understand, and there's a lot of work that needs to be done there. Okay, so using the same analogy, so one thing that's kind of interesting that many people have independently observed is that, well, if you kind of use this analogy and look at the brain versus kind of a database or a scratchpad type analogy, well, human intelligence is augmented by combining these things. And kind of using, a scratchpad as like a supplement to your brain's understanding. And by simply combining these two types of models, many people have found that hybrids tend to perform better than either of them in isolation. So this goes back to this model called H3, which was before Mamba. And then after Mamba, there's been lots of models, Jamba, Zamba, Samba, and probably a bunch more that I don't remember. And they all kind of are doing similar things by basically just interleave, like a more naive way of combining these, which is just interleaving attention layers and state space model layers, or Mamba layers specifically, as you can tell from the name. Yeah, so these have become very popular, and many groups have kind of independently verified using different setups, different model sizes, and so on, that interestingly, it's been pretty consistent that a 10-to-1 ratio of SSM layers to attention layers has seemed optimal, at least in terms of, say, perplexity. Downstream evaluations, as I said, can be a lot more difficult to really understand, but this is kind of a curious finding. And maybe has, again, using this course analogy, is kind of interesting because, like, if you were to a priori say what's the optimal combination of how much lifting your brain does versus having access to a database or scratchpad, probably you'd say your brain is doing more work, and having the database kind of supplements or augments that. And this seems to be reflected in the optimal ratios that people are using.
And it means like you have like 10 layers of an SSM, then 1 layer of a
Yeah, something like that. Yeah.
So just a question. This is at a fixed amount of compute. How do you do this comparison?
So I guess you can kind of ablate, like, yeah, using a fixed model size.
So a fixed model size, if it's 1-to-1, would be much lower than 10-to-1.
It would be much what?
Much slower to train.
So we're kind of not talking about the wall clock time of models here, but let's say that on relatively short sequences of like 1,000 or a few thousands, that these models have similar training speed. And so we're going to kind of ignore that. You can be more fine-grained in terms of the exact flock counts, but roughly speaking, let's say they're pretty similar. Attention is not too bad at short sequences, right? And so you can just swap out different layers and kind of ablate these. And so I think like an interesting question is these, a lot of people kind of point to the weaknesses, the obvious weaknesses of models with finite states like SSMs, and point to the obvious things that it can't do, like because they're compressed, they're so compressed, you can't do like, you know, recall, retrieval, and so on. I think it's an interesting question to ask, is that a bug or could that be a feature? Because perhaps compression is core to intelligence. You need to take information that you've seen, and instead of just shoving into a database, which doesn't really scale, you need to like cleverly summarize or turn these into more abstract representations that are more easy to manipulate, that contribute more to understanding. So this is kind of just a high-level thought that we don't quite understand at this point. Question?
So when you have these hybrid models, the transformer is operating in this representational space, like high-dimensional vectors, like 120-dimensional vectors. But the Mamba or the SSM architecture you're describing takes in scalar inputs. So do you apply it like component-wise? Is that what happens?
Yeah, great question. So I guess I accidentally glossed over that. But the models are defined with like scalar inputs and outputs, which is just how it's easy to define the model. But if you're given, you can work on arbitrarily long vectors as well by just operating channel-wise. And then you kind of, you can view it as that's the sequence mixing layer. And then there's going to be like, you can throw in MLPs and stuff that will mix across the channels. And that's kind of, yeah, that's enough. You don't need to like do them both at the same time.
Yeah, so I also have a pretty naive question. So when you come out of a SSM layer and you feed into an attention layer, what do you feed into the attention layer? The state?
No. So with the SSMs, you view them as, you view the state as like a latent representation that's helping you do this input to output map. But you don't actually need to materialize the state. I don't know where I define these, like here. So basically, you view this layer as a map from an input to an output. Remember, I define a sequence model as just a map from input to output sequence. The state space model defines this map implicitly through a latent space. But all that you need in terms of when you're like training these models as feed-forward sequence-to-sequence mappings is you feed in the input, you materialize the output. However you compute this mapping is up to your implementation choice. And in practice, you actually need to avoid materializing the state to be fast enough. But you just think of this as like, again, like they satisfy the same kind of interface. And so you can take any attention layer in transformer and just swap it out with an SSM that satisfies the same interface.
And when you come back to the next SSM layer, do you actually keep track of the previous state in the pre-attention SSM layer?
No. So each layer kind of has its own local state. Yeah. Okay. So I'm gonna move on because I'm running out of time. So also happy to chat after. Okay. So this is kind of a high-level question I ended on. Now let me talk a bit about so these are kind of like the trade-offs of SSMs. Now let me talk a bit about the trade-offs of attention. So attention is all you need, right? So it's everywhere. Transformers are remarkable, by the way. I love transformers. Like you can use them in lots of applications, and there's this kind of prevailing thought that you can basically just take data of any modality and kind of throw into a transformer, and it generally just works. So this is kind of true, but there's kind of some more subtlety here. So actually, the way I think about it is that attention, so a high-level claim or thesis that I have is that attention is only effective on data that has already been compressed into representations that are at the right level of abstraction. So I'll unpack this a little bit. This is a bit of a fuzzy concept that's hard to formalize. But basically, if you look at any actual end-to-end model that uses a transformer, it always has some encoding layers that are basically doing this compression of whatever original data you have into kind of features or abstractions that are amenable to being operated on by attention. So for example, transformers have now become commonly used in modalities such as images, videos, and other sorts of perceptual modalities. And these always go through some sort of process like patches, where this is kind of the most naive way you can do it, but you can just take your image, divide it into patches, turn each one into a representation, and then feed that in. And so the point is that each patch is kind of, compared to the raw data, each patch is trying to represent some higher level concept of like something in each patch. You hope that there's something semantically meaningful in it. And only at this level of abstraction is the transformer useful. If you were to operate directly on pixels, it would not be so useful. And this applies to all these other modalities as well. And then for modalities like language and other sorts of discrete modalities, such as, say, DNA sequences or so on, you'll often need to throw in a tokenization layer that basically takes your raw data and then splits it into basically shortens the sequence by splitting it into tokens. Each token is supposed to represent some sort of higher level concept that can then be fed into the transformer. Now, tokenization is something that we've all just kind of taken for granted, but many people kind of think is the root cause of all evil. Well, by many people, I mean Andre Karpathy, but a lot of other people don't really like tokenization, me included. And it's because you can kind of look at it and concretely look at all of these downsides of tokenization. Like your model loses fine-grained control over, spelling. Like it just isn't working on the character level, so it can't do things that require that. But more broadly, I think even philosophically, even if tokenization just kind of works in all of the systems we see right now, I think that there's kind of a, to me, kind of as a purist, I think it's not really the right way of doing things. And in machine learning, we've always progressed from kind of handcrafted features and more inductive bias to less and less, to more and more general end-to-end models, less feature engineering, less inductive bias. And that's kind of just the way models have improved. And that's kind of just philosophically the way that I think AI should be done. And so tokenization is an obvious issue with that. So we've moved from like all of these handcrafted features in NLP, like bag of words, n-grams, and so on, and slowly gone rid of them, and that's seen huge capability increases. But we still have relics that are clear feature engineering, such as tokenization. And what happens when you don't tokenize? This is a setting that used to actually be really important, and people used to investigate this. It's sort of been lost. But if you try to go back to, say, character level modeling, transformers actually just don't work that well out of the box. So Sasha Rush's group worked on this a little bit, where basically you're comparing the flop to efficiency or flop to performance of different models. And if you're trying to model autoregressively at a character level, there is actually a huge difference between transformers, and basically this is just Mamba out of the box, but I think it would apply to most of these other linear models as well. The reason is basically, well, okay, I think that's coming up. Running a bit out of time, so let me just try to get through the rest of this and I'll take questions after. Similarly, on other domains that kind of have fine resolution, such as DNA modeling, you can also try to train foundation models on DNA. This is something that people have only looked at kind of recently. And if you just use these models out of the box, Mamba scales actually a lot better than a very strong transformer. Okay, and so why is this? So basically, what makes for an effective token? So this is a bit, it's a bit hard to kind of formalize, but it's kind of clear from intuitively. So kind of, if you look at when should you use attention, you have to ask the questions, okay, obviously, like, when does it make sense to do pairwise comparisons over every token of my data? Another heuristic is like, attention uses the softmax thing. You can view it as an approximation to hard attention, which is, you can think of, when will I need to pay attention to one specific token in my past, right? And so kind of, if you're doing like language modeling, you kind of just think at the level of abstraction of words. And you won't really, like if you're reading something, you wouldn't pay attention to one specific character in the past. And so that's kind of why intuitively attention doesn't really make sense at a character level. Or kind of using this autoregressive state intuition, the question is, does it make sense to cache a separate representation for every token of data in the past or in my database? And once again, kind of having representations at the word level makes sense, but at the character level just seems obviously wasteful. And so that's kind of why, and there's kind of more intuition here, which is like, a good token for attention should kind of be intrinsically semantically meaningful. It should be kind of modular and composable, and that's when attention really shines. But if you don't have, and I don't really know how to formalize this, but it seems kind of clear. And if you don't have these properties, such as when you go to the character level, then it just doesn't really make sense intuitively. And the thing is, in language, it's easier to illustrate this, but in basically every other domain, there's no clear concept of what a token is. So when we go to like images, audio, and so on, this concept of patches as tokens just really is kind of fuzzy and nebulous. Like, are these things semantically meaningful? Are they composable? It's just very hard to define. And here you get to an intermediate area where we see that like these other models actually do really well in these other domains, which I think is related to the fact that there's no clear concept of token, which is what attention really needs. Not sure what you mean.
And that way it has like curves and lines and points.
Oh, okay. You mean, sure. It's kind of a different representation for images, right? I mean, we can talk about this offline, but I think obviously you can view data in different ways. But we're kind of, here I'm just thinking of the classic paradigm of images from pixels.
When I think about music, I don't think about.
Sorry, I'm out of time, so can I just finish this and we can talk in the break after? I don't mean to interrupt, but I just want to finish kind of the last thing I have to say. Okay, so there's other thought experiments you can sort of give, such as, okay, so we kind of had this sentence that attention operates very well on, but what happens if your data is not really perfect? Like, in normal speech, you have lots of filler tokens. Your data just might not be perfectly cleaned. And this is interesting because this is really the same sentence, the same information. But if you use a transformer on it, you're paying this insane overhead, right? Like, you're seeing twice as many tokens and actually no new information, but you're paying 4 times the cost. And this is all kind of related to, and you can wonder, is this related to why our models are so sensitive to data quality and so on? But more generally, these are all kind of different windows into this idea that unless the data is really formatted the exact right way for transformers, they have a lot of obvious shortcomings. And so this is just going back to this kind of central thesis that attention really is only effective when your data has already been compressed into the right levels of abstraction or tokens. And it's kind of interesting that we've kind of taken transformers for granted and have done a lot of work to modify your data in a way to fit the transformer. So we've just taken things like tokenization for granted that no one even questions it. But I think you can flip this on its head and say that really, like, we should be doing NN models from characters, from raw pixels or whatever, and we should be designing better models that can work with that in a more natural way. Okay, so I think I just have one final thought. Okay, and so as I was kind of saying, this is why these models have been really effective. Actually, language, not on language, but on every other type of modality, where this concept of tokens and representations and so on are much fuzzier. We've seen that models such as Mamba work just really well out of the box. Okay, so those are kind of the main trade-offs of attention. So obviously, it's very strong at recall, at fine-grained manipulation of the context, and it has weaknesses in efficiency. And so the last thing I'll say is that these downsides of attention, which are kind of often, it's just the way that people describe the downsides is this quadratic scaling problem, right? This is the way every paper talks about it, including mine, just because it's easy to talk about. But actually, I think this is not quite the right question to ask. So there's a lot of pushback on this idea because people say, oh, like, quadratic scaling isn't really a problem. You can, like, for one, you can engineer around it. You can just use more compute, and it's good enough in practice for the context length we care about. Also, this idea of you know, people look at quadratic versus linear and say, obviously, quadratic is worse, but that's just kind of not right, because what if your quadratic scaling or the additional compute you're using is just giving you better performance, right? So there's a trade-off between efficiency to performance that you need to always take into account. And so just looking at this so-called quadratic scaling isn't really the right question. What I think is the right framing of this is, so there's this popular view nowadays of foundation models, especially by big industry labs who train these models. They kind of view, a popular view is that models are basically a black box that you shove in flops, and then somebody described them as vehicles that turn flops into capabilities. And this is actually like the way that, all of these scaling laws that the big industry labs are training, all of this is basically, this is the core of the viewpoint there. And so with this viewpoint, basically the central question isn't about the exact scaling, the asymptotics, but simply this question, which is my model using its compute wisely? Is every flop that I'm throwing into my model actually important? And so from this viewpoint, I think this is where you really, at least the way I see that the obvious downsides of transformers, which is that through kind of a lot of these illustrations that I've given with sort of these different examples, there's just many, many cases where it's obviously not using its compute wisely. It's caching representations unneeded that are unnecessary, or doing all these comparisons that are just obviously not useful. And this is kind of fundamental to attention, in my opinion. And so this is the central question to ask. And I think we don't have perfect solutions for this, neither state space models or attention. And there's still a lot of work to be done here. Okay, so I'll end here. Sorry, I went quite a bit over, but happy to take questions afterwards.
Let's take Alfred, and maybe let's take questions. We'll be back in, let's say, 10 minutes. 10 to 5.